To our new webinar series on extreme events and hazards. I am Margaret Boone, Program Manager with the Southern Climate Impacts Planning Program, and I will be the moderator for today's webinar. Alec Krautman, SCIP Research Associate, will be managing the webinar. This webinar is part of a series of webinars that will focus on extreme climate and weather events and hazards that affect the southern United States. Our previous webinars have discussed hazards such as hurricanes, flash flooding, and severe weather. But the topic of today's webinar, most appropriately, is winter weather. Presenters for today's webinar include Rick Smith, Morning Coordination Meteorologist with the National Weather Service Office in Norman, Oklahoma, who will give an overview of winter weather forecasting. Sid Sperry, Director of PR, Communications, and Research with the Oklahoma Association of Electric Cooperatives, who will discuss OAEC operations as well as the Sperry-Piltz Ice Accumulation Index, which he co-founded. And Carly Kovacik, a recent master's degree graduate from the University of Oklahoma, who will present some of her research findings regarding Oklahoma ice storm frequency and teleconnections. I'd like to briefly discuss the goals of this webinar series. We plan these in order to provide timely and relevant weather and climate hazard information to our local, state, and regional organizations, agencies, and business officials who are directly affected by these various extreme events and hazards. We strive to make the information seasonally relevant, and what a better time to discuss winter weather than right before this next weather system that is forecasted for this weekend across the Southern Plains. Also, for those who have called in to today's webinar, if we can just make sure that unless you are presenting, that your phone remains on mute, we would really appreciate it. So at this time, I would like to turn it over to Rick Smith with the Norman Forecast Office.
Okay, thank you. Good morning, everybody. Hopefully it's morning for most of you. It's afternoon maybe for some of you, but glad you could join us today. I'm going to talk very briefly about an extremely complex topic, forecasting winter weather. 15 minutes won't begin to scratch the surface, but I really want to just kind of introduce you to, or remind you, or tell you about some of the challenges associated with forecasting winter weather. Winter weather forecasts come from a variety of places now. Need to get closer to the mic. I'm going to try to do that here. Hopefully this is better. Winter weather forecasts come from a variety of places. They used to just come from the Weather Service or a TV station, but now you get them from those places. You also get them from social media. Any 13-year-old with a computer and an internet connection can have their own forecasting service and post model output to their heart's content. And that's good that it's easy to share weather information, but it's also a challenge for us in the weather business because it's easy to get confused. There's a lot of information out there. I'm going to talk primarily about what we do at the National Weather Service and our network of offices across the country. There are 122 local forecast offices, and if we zoom in kind of to the southern climate area here, we see there's a variety of offices. There's actually 13 offices that serve the state of Texas. There are 4 different offices that serve the state of Oklahoma. So no matter where you are, what city or county you're in, you're covered by a local forecast office that's staffed with local weather experts and forecasters who are as familiar as they can be with your local weather patterns and the intricacies of winter weather forecasting. And I can tell you, having worked in several of these states, that it's not easy in any of these places. It seems like it's always a challenge, precipitation type and things like that. There's also a national component when it comes to winter weather forecasting, and that's the Weather Prediction Center, formerly known as the Hydrometeorological Prediction Center. But the WPC does winter weather forecast, and they have a wealth of information on their webpage related to ice storm or ice accumulation forecasts, snow forecasts, and things like that. So we work hand in hand with them. We use the guidance they provide us to help us do our job, and that information is also available publicly on their website. So the main challenge with precipitation forecasting is almost always the precipitation type. What's going to fall? Is it going to be sleet, snow, freezing rain? And it's hard. It's a combination of, obviously you need precipitation to fall, but you also need the right structure of temperatures, not just at the surface, but vertically through a large depth of the atmosphere. So when we're doing a winter weather forecast, we're having to look in 3 or 4 dimensions actually in time, and then in the vertical and in the horizontal. And this is just one example of one of the many tools that we use to do a forecast. There's many different methods, many different methodologies that the forecasters use, but I just picked this slide to kind of show you some of the complexities involved with determining exactly what's going to happen. Not to brag a little bit, I mean, we get it right every once in a while. No, more than that, but I'm proud of our office for what we did with the last winter storm. The left is the forecast of what we had as far as amounts, and the right is what actually happened. Are the amounts exactly the same? No, but the general pattern is pretty good, where the snow fell, where the heaviest snow fell. And that's one of the things that we tell people in our area is not to get so hung up on those exact numbers. People love numbers, and people love to get hung up on, are we going to get 3 inches or 4 inches? But in a lot of cases, it's just not possible, especially days in advance, to tell you exactly how much is going to happen and where it's going to happen. One of the key things we use in winter weather forecasting is knowing the three-dimensional vertical structure of the atmosphere. Where's the moisture? Where are the ice crystals forming? Where are the temperatures below freezing? And the only real direct way that we have to do that is through upper air releases, or weather balloons. And this is a picture of a weather balloon being launched outside our building. And the plot that we get back is in the bottom right corner of the screen there. That's a skew T diagram, and that's if you're not familiar with that, it's a bunch of lines and very complicated looking, but it can tell us a wealth of information about to get us started on the precipitation forecast. These weather balloons are launched twice a day, every single day of the year, at about 92 sites across the United States and over 800 worldwide. We try to coordinate those at the same time. And if we zoom in on kind of the southern area here, you see that there's not a lot of them. I mean, these things are spaced out a few hundred miles. And you know from where you live that the weather in Norman, for example, can be dramatically different than it is in Moore or Oklahoma City or Purcell or just a few miles away. So having the weather balloons spaced this far apart is a challenge when it comes to winter weather forecasting. And the fact that we only have them launched twice a day makes it even that much more complicated. So that's fine. That's one of the challenges. When those weather balloons are launched, it gets fed into our main computer system, the data, and as those balloons are rising, every few seconds they're feeding us back information on the temperature, the humidity, the wind, as it goes up through the atmosphere. All that information is fed in with other information into supercomputers that spit out model output to give us a computer simulation of what those models think is going to be happening over the next hours, days, or in some cases, parts of couple of weeks out. And there are many, many different models. And this is just a snapshot of a few of the different kinds of model output that we see. One of the things that we use a lot in the Weather Service and a lot of forecasters use is something we call ensembles, where weather models are run multiple times with minor changes to certain parameters in that model. And we look for kind of convergence, or, if you look in the bottom right-hand corner there, you see those are some model computer predictions of what a weather balloon would look like if we launched it at some time in the future over Norman. And the closer those lines are together, the more agreement those different members of the model ensemble group have, and the more confidence we have. But a lot of times the spread, it looks like those hurricane charts you see, there's just spaghetti all over the place. So it's not often that we get really good agreement in all the models, but there are many different models. And what you need to be aware of on the internet and on social media especially is a lot of people that aren't familiar with winter weather forecasting will just pick kind of, the highest numbers or the biggest, most dramatic looking things and post those. So you need to be very cautious in how you use your weather information, where you get your forecast from, because, it's not always that worst case scenario, fortunately. So the trick always becomes, are we going to be dealing with freezing rain, sleet, or snow, or rain? I didn't put rain up there. But really the difference in that, the difference in whether your kids go to school or not, the difference in whether the road crews are working overtime or not, is 1 degree of temperature, hundreds or thousands of feet above the surface. And the only way we have to know what that is why weather balloons launch twice a day, 200 miles or more apart. So it's a challenge. It really is. And I didn't come on here to whine and say how tough our job is, but it is tough. And so winter weather is the toughest thing that we have to deal with here. Just really quickly, that I mentioned that vertical structure of the atmosphere. One of the things that we're analyzing when we're looking at observation data or computer model data is what is the vertical structure. So, and this next series of diagrams is going to kind of break it down. In the diagram that you're looking at, there's a vertical blue line there. That's the 32-degree or the freezing line. So everything on the left of that, the temperature is below freezing. Everything on the right of that, it's above freezing. And this is what we would look for if we were forecasting freezing rain. In this case, all the precipitation forms up, miles above our heads and starts falling as snow. At some point, there is a warm layer in the atmosphere where that snow melts and becomes liquid water, becomes rain again. In a freezing rain sounding, the below freezing temperatures in a very shallow layer right near the surface. So a lot of times the rain does not have time to refreeze before it hits the ground. So that rain falls as liquid, but it freezes on contact as it hits power lines and antennas and bridges and overpasses and things like that that are below freezing. And I think Sid's going to talk about that in more detail, because the next slide, this is what happens with freezing rain. And freezing rain is, I do not like it at all. It's a problem, and we get enough freezing rain. We have an ice storm where we have debilitating power outages, and tornadoes are horrible in the damage they produce, but ice storms, in a way, are worse as far as their aerial impact and their long-lasting impacts. People can be without power for considerable periods of time with ice storms. What's easier for us, which almost seems to never happen around here, is just getting snow, where you see everything, that vertical temperature profile, everything's to the left of the freezing line. So all the way up in the atmosphere, everything is below freezing. So it starts to snow up in the upper cloud layers miles above our heads, and it's snow all the way down. That can happen, but it seems like there's often a transition zone where we're on the edge of that. And finally, sleet is kind of in the middle of that. There is a warm layer when we have a sleet sounding, but it is less deep or more shallow than it is with the freezing rain. That means that as that snow falls, it falls into the warm layer, it melts and becomes liquid water, but then there's a deep enough layer of cold air before it gets to the ground that it has time to refreeze into those little pellets of ice that we see. And those can have their own issues as far as travel and having to pick your way out of your garage and things like that if you've ever had to deal with a whole lot of sleet. So anyway, those are the challenges. So our job in the Weather Service is to share that information with you and talk about what we think is going to happen. We have 4 main ways to do that. The outlook. An outlook is just something that's looking out days in advance. It says something could happen. We could have a winter storm 3, 4, or 5 days from now. We don't know exactly where, when. We don't know exactly how many inches or if it's going to be ice or snow. But it's a heads up message telling you to be ready. When we're more confident, when the confidence has increased on everything, then we'll issue a watch. And this is usually a winter storm watch. That may be issued 12 hours in advance. We have even issued them further out than that in advance. It means that our confidence has increased, the risk has increased, but there's still considerable uncertainty. A lot of times when we issue a watch, we're still not certain exactly what time it's going to happen, exactly the location of the heaviest band of snow, but the watch is a more serious message to give you information telling you, okay, we're a little bit more sure now that this could happen. The winter storm warning, or the most urgent winter weather message we have, is an ice storm warning around here. That means it's either already occurring, hopefully not, but it means that it's highly likely. So we try to get that warning out as far in advance as we can. So you might get a winter storm warning or an ice storm warning 24 hours or more before the event begins. And the warning is the most urgent message telling you that, a winter storm warning or an ice storm warning means that we expect there would be enough precipitation, enough impacts to cause serious inconveniences to your life and possibly dangerous or deadly conditions if you don't pay attention to that. If you wait until the warning is issued to go make your milk and bread run, you probably waited too long. So, personal experience, I'll tell you that. Winter weather advisory is kind of a junior warning in a way. It's for situations where we don't think it's going to be a real threat to life and property. It's not going to shut down commerce and travel and knock out power for thousands of people, but it's going to be more of an inconvenience or a nuisance type event. And that might be a winter weather advisory. And I bet we'll have winter weather advisories for parts of our area by tomorrow night or Saturday, because we're expecting some freezing rain and some snow. So it's just to tell people that, you know, this precipitation is happening, and be careful. It's in a lot of all of our local TV stations still refer to these as travelers advisories, although travelers advisories were done away in the Weather Service in the 90s sometime. That's essentially what these are, though. These are mainly for people that are traveling or walking on icy sidewalks and things like that. And I know we're going to take questions at the end, so that wraps up my portion, and we'll hang on to your questions, and we'll get to those at the end here.
Thank you so much, Rick. I think that was a great overview of just how complex it actually is to try to forecast all the different precipitation types in winter. And it gives us, I think, a much better appreciation for what you have to do as a forecaster when you're making these very difficult decisions on what to tell everybody. Okay, next we'd like to hear from Sid Sperry, Director of PR, Communications, and Research with the Oklahoma Association of Electric Co-ops. Sid?
Thank you, Margaret, and thank you, Marcia, for inviting me to participate in this webinar. Let me start off by saying, while I've got our association cover slide there, just to echo what Rick has passed along, and that is that we at our association certainly appreciate and value the work that the folks at the National Weather Service do. Those of you at SCIP and all of the participants understand that forecasting the weather is not an easy chore. I will make this statement. Rick knows this. The folks that I work with, I am not a meteorologist, nor do I pretend to be. You folks have done a great deal of work, and your education and background and dedication to the weather is far superior to anything that I might know, but I value what you do, and I appreciate everything that you do. So with that, I'll just give you a little bit of information about our association and why weather, and in particular winter storms, are such a concern to us. So we'll move on to the next slide. A little bit about our association. We do have a total of 30 electric cooperatives in the state of Oklahoma. 28 of those are what we call distribution cooperatives, meaning electricity is generated by the G&Ts, which that stands for Generation and Transmission Cooperatives, and then is shipped out, if you will, over high voltage transmission lines to substations all across the state. And in Oklahoma, as you see from the map there, we have 28 different cooperatives across the state of Oklahoma. We are the only utility entity that serves collectively in all 77 counties of the state of Oklahoma. No other utility does that. So obviously, from a weather standpoint, we're concerned about what happens out in Cimarron County in the Texas or in the Oklahoma Panhandle to McCurtain County in the far southeastern part of the state, and all points in between. We do serve collectively over 500,000 consumers, and something else that gives you an idea about our exposure to the elements. We have over 106,000 miles of distribution power line, another 15,000 miles of high voltage power line that our members own and maintain. So that number that you see there, 106,000 miles of distribution power line, probably 95% of that is overhead because of the expanse that we have to reach and provide service to. That number is more than OG&E, Public Service Company of Oklahoma, and the Municipal Electric Systems of Oklahoma combined, to give you an idea of the length and miles of line that we have to maintain and oversee. Next slide. Again, just from an association standpoint, so folks know a little bit more about who we are. We do have over 2,300 people that work at our cooperatives collectively across the state of Oklahoma. Nationally, there are just under 1,000 electric cooperatives, and they employ about 170,000 people. Next slide. What we do here, essentially, with OAEC, we've been in existence since about 1942. founded specifically as a voice for electric cooperatives and primarily for the folks in rural areas that receive their electricity from electric distribution cooperatives. We like to say that we do collectively what our individual electric cooperatives would not be able to do, both economically or from a political standpoint. We do have one arm of our association that's a lobbying arm, a political arm that represents us and our cooperatives and our consumers, quite frankly, at both the state capitol here in Oklahoma City and in Washington, D.C. One of the things that we do is provide a variety of services, and I think on the next slide we'll go into that just a little bit more. As far as research and technology is concerned, I would be the first to say that we are an ardent supporter and promoter of the Oklahoma Mesonet. Beginning in the early 1990s, we began what I'd like to consider an alliance with the folks from the Mesonet, because we realized early on that the importance of weather forecasting and actually being able to watch live radar from each one of our cooperative offices across the state on a 24-hour day, 365-day-a-year basis was extremely important. I'll talk a little bit more about the Spia index on some slides to come and how that came to be, but just to give you a little bit of an idea of what branches of research and technology we are involved in. We are active with the Oklahoma Wind Power Initiative, with the Environmental Verification and Analysis Center there at OU. Several of our cooperatives are involved in research on fuel cells with the Cooperative Research Network and also the electric power research industry. We do have an active partnership with Oklahoma State University with earth-coupled heat pump technology. We have several of our cooperatives that also have online outage management systems. And coming soon, we hope, within the next few months, we hope to have a statewide outage map representing all of our cooperatives collectively. So much like you see with some of the larger utilities across the nation, folks would be able to track outages that our cooperatives might be experiencing. Next slide. Let's talk just a little bit about this thing that's called the Spia index, and that does stand for the Sperry-Piltz Ice Accumulation Index. And just to give you a little bit of an overview of how that came to be, actually this tracks back to December of 2006 when the Oklahoma Panhandle was hit with back-to-back winter storms. Ice events occurred within 7 days of each other that did quite a bit of damage. And of course, as many of you may know, Oklahoma seems to have been beset over the last 12 or 13 years with a number of severe icing events. Ones that I can remember specifically were the Christmas Day ice storm in 2000, and then again in January of 2002, a very severe icing event happened in northern and central parts of the state of Oklahoma, then again in 2007. But shortly after the back-to-back ice storms in the Panhandle in 2006, I drove down and visited with the folks at the Oklahoma Climate Survey in Norman. And the idea that I had was to see if it might be possible to couple the forecasting technology that the National Weather Service has with degrees of impact as far as electric utility systems and, quite frankly, communication systems all across the state and region were concerned. I have about 33 years of working in the electric utility industry. I can tell you, being a former lineman, I have a lot of experience with knowing how much ice and how much wind it takes to begin to do damage to not only electric distribution systems, but also transmission networks as well. These are very reliable systems, but when they are faced with certain amounts of ice and coupled with certain amounts of wind, we know the threshold at which damage begins, and we've got a lot of data to support that. So essentially, This index, with the help of the folks at OCS, we began to sit down and put together an algorithm, and then with the help of both the folks at the National Weather Service office in Norman and also with Steve Piltz, the meteorologist in charge at the Tulsa office of the National Weather Service, we did develop what's now known as the Spia index, which is a forward-looking ice accumulation and ice damage index. I might also add that there are currently 10 National Weather Service forecast offices that are using the index on an experimental basis across the country. I think I can recall that those are Tulsa, Norman, Springfield, Missouri, Kansas City, Missouri, St. Louis, Missouri, Little Rock, Arkansas, Memphis, Tennessee, Nashville, Tennessee, Jackson, Mississippi, and Paducah, Kentucky. So those 10 locations are currently using the Spia index on an experimental basis and as a part of some of their decision support products. Next slide. Back to what Rick said about forecasting, and we certainly here at OAEC realize how difficult winter weather forecasting can be. I marvel, quite frankly, at how accurate the forecasting is with thunderstorms. And ideally for us, quite obviously, those type of forecasting accuracies would be wonderful if they were on the winter weather side, and I know how difficult that can be to make them that way. Rick will recall that as far as warnings and considerations for making people aware of what might happen, say ahead of the more tornadoes, beginning 5 to 6 days in advance, information was being shared from the National Weather Service to prepare people for that kind of an event. Certainly, that was a devastating event. From a utility perspective, we want to be able to give our utilities as much time as possible to prepare for a winter weather event, particularly an ice storm. And that's really what the index was created for, was to help utilities and communication utilities and other disaster preparedness entities such as Red Cross and Salvation Army, those that use sheltering, that kind of thing, to help prepare them for an approaching ice storm and to raise their level of readiness so that they could respond more quickly. That's really how the Spia index came about as a preparedness tool. And yes, I'll be the first to admit, we are very dependent on the National Weather Service forecasts. We understand when a forecast can go awry. We get that. But as far as having that information for us, from our perspective, if instead of having that information available to us, say, 2 days out or 48 hours out, if we had a better idea of what the forecast might even be getting to look like, say, 72 hours out, that would be a great benefit to us because it gives us an extra day to prepare. We do understand that the forecast can change and we can adjust accordingly. Next slide. This is the actual index itself, and I would be the first to tell you I'm not a very complex person. You might know that if you recognize some of those colors, anytime you travel after 9/11, you notice that TSA has implemented a threat level. And essentially, this is where the idea, as far as the colors are concerned, came from. I really don't get too concerned when I see the first two colors there, the first three, a 0 being green, a level 1 index prediction being yellow, and a level 2 being orange. Those are fairly minimal as far as damage to infrastructure is concerned, but I do begin to have concerns, as should anyone, when they see a level 3 in red or level 4 colors in purple. And quite frankly, how level 5 came about was if there's a level 5 event and that begins to be seen in the graphics, that indicates to me that power could be out for an exceptionally long period of time. When power is out, it's dark, and so the color black was used to indicate that. Like I said, I'm a pretty simple guy. It doesn't much more simple than that. The wind and ice fields that you see in the middle are averages that we use through our algorithm. We do begin to look at ice accumulation as low as 1/10 of an inch. Wind speeds only go up greater than 35 miles an hour in our wind fields because you actually can have damage to a utility system when there's only 1/10 of an inch of ice and a strong 35 to 40 mile an hour sustained winds, because that begins to cause what we call galloping on power line. It won't do a tremendous amount of structural damage as far as breaking poles and that kind of thing, but even that small amount of ice and that amount of wind, when coupled together, can cause some minor structural damage, which leads to some outages. As far as the damage and description impacts, those impact descriptions are contained on the right. And yes, these are general in nature. They're perhaps a little bit broad to be inclusive of the type of outages that could occur. And we'll talk a little bit more about that as we go into the next slide. But just so you'll know, the levels where we get very concerned are when we begin to see levels 3, 4, and 5. Now, these graphics that you see here, and to give you a little bit better idea of how the index actually works, we take the National Weather Service forecast for total ice from their ice grids, their digital grids, and we couple that with the max sustained wind forecast. It's important to note that we use max sustained winds, not wind gusts, because if wind gusts are used, that would tend to drive the index up about 1 to 1.5 levels more than what the actual damage would indicate. So that's why we use sustained winds, and most of you probably with some background in meteorology would understand why we would use sustained and not gusts. We're more concerned about the levels of winds as they exist at a steady rate. So when you take the total ice forecast and the max sustained winds and plug that into our algorithm, then you would see either a level 1, 2, 3, 4, or 5, and that's what you see in the bottom right graphic. These are actually images that were taken from Norman's experimental Spia Index webpage a couple of days ahead of the December 5th through the 7th event that we saw just about 2 weeks ago. Next slide. I'm going to be using on these next couple of slides the images for total ice and max sustained winds from the Tulsa office of the National Weather Service, only because it was primarily in their forecast area that the greatest amount of structural damage was done with this icing event that occurred last week. You can see at the bottom, again, this was a couple of days out, actually about 3 days out. In far southern Choctaw County, almost an inch of ice was in their grids. The max sustained winds for that area were out of the north at about 21 miles an hour. And if we go to the next slide, you can see that our index was predicting a fairly large path of what we would call level 4 there in purple, and some isolated areas of that carried a level 5 potential as far as structural damage to overhead power lines and overhead communication lines. Even cell towers can have a lot of issues when that kind of ice and wind are combined in the forecast. So you can see the path there that we were concerned about 2 to 3 days ahead of time. Fairly large area in red there of potential outage times in the 1 to 5 day range. A fairly large path of purple, a level 4, indicating that outages could go past 7 days, and in areas where the damage could have been heaviest in black, a level 5, it would be possible to see outages that were 10 days or longer. So if we go to the next slide, we can see, and I believe this is the last slide, Rick was talking about accuracy and forecasting, and believe me, folks, these folks get it right at the National Weather Service, and that's one of the things I so appreciate about them. we depend on that forecast accuracy. So 2 days ahead, National Weather Service office in Tulsa was looking at just over an inch, 1.08 inches of ice in southern Choctaw County, up into northwest Arkansas, almost a half an inch of ice at 0.49 inches of ice. And this is about 2 to 3 days after the storm. We received observed ice reports from observers that have measured the ice, so that gives the National Weather Service good feedback on just the amounts of ice that were reported out there. And you can see that those compare very favorably to what was being forecast. Before I leave this slide, I will tell you that we actually had one cooperative in far southeastern Oklahoma that serves much of Choctaw County, Pushmataha County, southern LaFleur County, and all of McCurtain County that was impacted by this storm. They lost over 550 wooden pole structures in this icing event because of the ice that occurred and combinations of wind there. And their damage collectively from 4 different cooperatives in the southeastern part of the state, their damage right now is totaling about $2.2 million from that icing event. Quite frankly, this was closer to a level 4 as far as the index is concerned, but there were some areas of level 5, as you could see from the previous graphics. And so having that kind of information well ahead of time help prepare the utilities for what might be coming at them and how they could better respond. And like Rick, I'll take some questions at the end. Thank you very much.
Thank you, Sid. I think that was a great overview, not just of OAEC, but the value of the Spia index that you helped develop. And I think we can all say we look forward to see more use of it in the future. Now we'd like to move on to Carly Kovacik, a recent graduate here at the University of Oklahoma, who's going to talk to us briefly about her research with ice storm frequency and teleconnections. Carly?
Thanks, Margaret. So over the past 2.5 years, I've been busy developing a preliminary climatology of ice storm frequency across the United States. And I've been working closely with Sid Sperry of OAEC on developing another climatology of Oklahoma ice storm frequency and comparing that to phase changes in teleconnections. Next slide, please. You go ahead and move again. Thank you. There are various impacts associated with ice storms, perhaps the most destructive one being the power outages, as oftentimes people have to seek alternative forms of living during this time. However, if people do so choose to stay in their homes throughout the extent of a power outage and use generators, they run the risk of carbon monoxide poisoning if they use the generators improperly. It also goes without saying that there's a lot of infrastructural damage associated with the power outages. Another impact from ice storms is aircraft icing, which is mainly due to the presence of freezing drizzle aloft, where sometimes freezing drizzle can rapidly accumulate on top of aircraft, causing severe degradation of aerodynamic performance, and in some cases has led to some accidents. Other impacts associated with ice storms include traffic disruptions and accidents, business closing, agricultural losses, and pedestrian accidents. Next slide, please. Next. I just want to briefly go over some of the methodology that I used during my thesis. I began by developing my own definition of an ice storm, and I'll show you why in a little bit. So I documented all of my ice storms by defining an ice storm as a winter weather event containing freezing rain that cause negative impacts regardless of the amount of ice accumulation or the presence of other precipitation types during the event. Next slide. There were 2 temporal scales that I used during my study. The first being a seasonal time scale where I documented all of my ice storms between December and February of each season. Literature argues that these are the coldest months for regions east of the Rocky Mountains, where ice storms tend to be most common. The other temporal scale was my yearly time scale, in which I chose to document ice storms between the periods of 1966 and 1977 and 1998 through 2011. Next slide. I chose these 2 time periods because of this graphic, which shows the annual global temperature anomalies associated with ENSO between 1950 and 2012. El Nino is shown in red, La Nina is shown in blue, and neutral seasons are shown in gray. So we can see prior to about 1978, La Nina was associated with negative global temperature anomalies, and after about 1978, we see it become associated with positive global temperature anomalies. And throughout time, we can see El Nino becoming associated with more positive global temperature anomalies. Next slide. So I decided to choose two time periods to kind of reflect this change. And so, next slide, I will begin showing the actual results from the ice storm climatology. So this slide shows the total number of winter ice storms that were documented between 1966 and 1977. Here we see the maximum is located in the northeast United States, especially in parts of far southern Maine, eastern New Hampshire, and far northern Massachusetts, where over 30 ice storms were reported. Secondary maxima are also seen, although less intense, across portions of Maryland and Delaware, the Appalachian region of Virginia and North Carolina, and in the central United States, we see a maximum in eastern Oklahoma. And as we go westward towards the Rocky Mountains, we begin to see the ice storm frequency decrease, with the exception of the Columbian River Basin in the Pacific Northwest. Next slide, please. Shown here is the total number of winter ice storms that were documented between 1998 and 2011. Again, we see the maximum located in the northeast portion of the United States. However, it's located somewhat more southward and westward than the previous period. Here, the maximum was seen across eastern Pennsylvania into northwest New Jersey, where over 30 ice storms were reported. We see a secondary maximum located in the Adirondack and Catskill region of eastern New York, where between 25 and 30 ice storms were reported. We still notice a higher frequency located in the Appalachian Mountain region, and we also see what looks like an increase in ice storm frequency across the majority of the Midwest and the Southern Plains. And again, as we move westward towards the Rocky Mountains and the western U.S., we see a decrease in the ice storm frequency, with again the exception of the Columbian River Basin in the Pacific Northwest. Next slide, please. So what I did next was I took a winter ice storm difference, where I took the total number of ice storms that occurred between 1998 and 2011 and subtracted this from the total number of ice storms between 1966 and 1977. So the warmer colors indicate a higher ice storm frequency between 1966 and 1977, and the blue colors indicate a higher frequency between 1998 and 2011. So what we see is a distinct westward and southward shift in ice storm frequency across the northeast United States. In addition to this, you'll also notice a lot of bluer colors across a majority of the Midwest and the Southern Plains, indicating that ice storm frequency has increased in recent decades. So as for my thesis in particular, this was kind of the turning point for my research, where I hypothesized that such a distinct westward and southward shift in ice storm frequency across the Northeast was due to meteorological sources, perhaps teleconnections that affect that particular region. I also hypothesized that what looks like an increase in ice storm frequency across the Midwest and Southern Plains was due to improvements in ice storm reporting. So for my thesis, I decided to focus on the Northeast, but when I was working with Sid Sperry at OAEC, we decided to take a look at Oklahoma just to kind of see how ice storms have changed over the past several decades. Next slide, please. Now I'm going to get into the ice storm frequency on a decadal scale across only Oklahoma. So shown here is the average number of winter ice storms in Oklahoma between 1966 and 1969. So what we see here is the entire state averaged around one ice storm during these several winter seasons. However, there's a slightly higher frequency that was noted across the Oklahoma Panhandle into the northwestern portion of the state and several isolated areas of northeast or east central Oklahoma. Next slide. So here's the average number of ice storms that occurred during the 1970s. Here we see that all counties in Oklahoma averaged about one ice storm during this decade. Next slide. Here we see not much change. This is the average number of ice storms during the 1980s. And again, all of Oklahoma averaged around one ice storm during the 80s. Next. So here is the average number of ice storms during the 1990s, and we see a slightly higher frequency across most of the state compared to the 1980s and the 1970s. The Oklahoma Panhandle and most portions of western, central, northern, and eastern Oklahoma averaged around 2 ice storms during the 1990s, with the exception of parts of the southeast Oklahoma, where the average is around 1 ice storm. Next slide. Shown here is the average number of ice storms during the 2000s, and we see that the spatial extent of the higher frequency has somewhat diminished. However, all of the state has still experienced around 1 ice storm during this decade. Portions of western, central, and northern Oklahoma did average around 2 ice storms during this decade. Next slide. Now I'm going to show a few comparisons of the ice storm frequency with selected teleconnections. I chose to look at ENSO, and in case anyone is unfamiliar, I just want to briefly go over the typical conditions associated with El Nino across the United States. There's a lot of subtropical jet influence in the southern United States during El Nino, and particularly across Oklahoma. Conditions are usually wetter and a little cooler than average. So next slide. So with this shows the average number of winter ice storms in Oklahoma during El Nino seasons between 1966 and 2011. So what we see again is most of the state has averaged around 1 ice storm when El Nino is present. However, portions of western, central, and into parts of northern Oklahoma did average around 2 ice storms when El Nino was present. Next slide. La Nina conditions are usually associated with opposite conditions as El Nino, at least across the southern plains of the United States. Typically in Oklahoma, conditions can be drier and warmer than normal. Next slide, please. So here shows the average number of winter ice storms in Oklahoma during La Nina seasons between 1966 and 2011. Again, most of the state averaged around 1 ice storm, and we see several dots of around 1 to 2 ice storms, and that I think is due to just differences in reporting. So next slide, please. And so neutral conditions, typically across the southern plains and around Oklahoma, conditions are wetter and warmer than normal. So next slide, please. We see here shown as the average number of winter ice storms during ENSO neutral seasons between 1966 and 2011. Here we see some similarities to the El Nino graphic, where all of the state has averaged around 1 ice storm, but several portions of northwest Oklahoma into central Oklahoma into northeast Oklahoma did experience an average of 2 ice storms during ENSO neutral seasons. So comparing the 3 seasons together, it looks like when El Nino seasons or El Nino conditions are present or ENSO neutral conditions are present, there seems to be a slightly higher average number of ice storms across Oklahoma in the wintertime. So next slide, please. I also chose to look at the Arctic oscillation and how that affects ice storm frequency across Oklahoma. The literature argues that the temperature in the Midwest and Southern Plains is affected by the phase of the Arctic oscillation. So shown here are the conditions when a negative Arctic oscillation is present. And when this occurs, there is higher than normal pressure over the Arctic, which ends up weakening the jet stream in the upper atmosphere, which allows colder Arctic air to penetrate south into the United States. And typically, Oklahoma experiences cooler than normal temperatures. Next slide, please. So shown here is the average number of winter ice storms in Oklahoma during negative Arctic oscillation seasons between 1966 and 2011. Here we see that the entire state averages around 1 ice storm. Next slide. Shown here are the conditions associated with a positive Arctic oscillation. During this, there's lower than normal pressure over the Arctic, which allows the jet stream to strengthen and keeps polar air confined to higher latitudes. When this occurs, Oklahoma and the southern plains usually experiences warmer than normal. Here we see that all of the state averages around 1 ice storm, or most of Oklahoma actually experiences an average of 2, with the exception of southeastern Oklahoma. So between the 2 phases of the Arctic oscillation, it seems that there's a slightly higher frequency of ice storms when the Arctic oscillation is positive. Next slide, please. So, as I just stated, we see that there's a slightly higher frequency in ice storms across Oklahoma when El Nino conditions are present and positive Arctic oscillation conditions are present. So what I then did was I averaged the number of ice storms in Oklahoma when El Nino conditions are present with both positive positive Arctic oscillation periods. So what we see here is all of the states average around one ice storm when these conditions are present together. However, there are portions of southwestern, west central, central, and northeastern Oklahoma where the frequency is slightly higher with an average of around 2 ice storms. Next slide, please. I did the same thing for La Nina and negative Arctic oscillation conditions. So when these two conditions are present together, we see that Oklahoma averages around 1 ice storm. Next slide, please. And if anyone is curious about the Northeast United States, I conducted the same type of study, except I included the North Atlantic Oscillation and the Atlantic Multidecadal Oscillation in my study. And what I found was that when El Nino is present with a negative AMO, that there's a higher frequency of ice storms that occurs in the northern portion of the Northeast, particularly across southern New Hampshire and southern Maine. And when La Nina conditions are present with positive AMO conditions, the average number of ice storms is highest in the southern portion of the Northeast, particularly across eastern Pennsylvania, northwest New Jersey, and eastern New York. Next slide, please. So there were a few headaches encountered when doing the data analysis during the study. The first one being the definition of an ice storm. There exist a lot of inconsistencies across the National Weather Service weather forecast offices, where many offices use supplemental criteria in addition to the nationally followed ice storm definition that's currently set. And in addition to this, there's no sustained long-term way to measure ice accretion during an event. A lot of times observers will measure ice accumulation on any available surface or where they think that the ice accumulation is thickest. However, it must be kept in mind that ice will accumulate on surfaces differently, and this is due to different thermal properties of surfaces, along with the orientation of the surface during the event and the wind speed. So with these two inconsistencies, ice storm reporting is rather challenging and somewhat contains inaccuracies. And in addition to this, the instruments that measure freezing rain also have their limitations, and this is especially found in the probing instruments of each ASOS site. Next slide, please. So several main conclusions and things that I want everybody to remember before I finish up. The most important being what I just went over, that there lacks a unique definition of an ice storm or a way to measure ice accretion at the moment. So a nationally based definition of an ice storm and way to measure ice needs to be implemented before any accurate climatology can be developed. I will say that I used storm data for my thesis project, and that there were inconsistencies associated with both the definition and way to measure ice storm accumulation that it definitely skewed some of my results. But qualitatively, the results do suggest that there may be a change in ice storm frequency across the Northeast and possibly across the Midwest and Southern Plains. In addition to this, across Oklahoma at least, ice storm frequency was found to be higher during El Nino seasons or positive AO seasons, or when El Nino is coupled with positive AO. And across the Northeast United States, ice storm frequency tended to be higher when El Nino is coupled with a negative AMO and La Nina is coupled with a positive AMO. So with all of this, I want everyone to take these results with a grain of salt. However, I do think that there is some important meaning behind it. So I will gladly take any questions anybody has about this.
Thank you, Carly, for presenting your research, and thank you actually an extended thank you for joining us so soon after you're defending your thesis and while you're on your break. And I want to give a thank you to all of our presenters today. And now I would like to open it up for any questions or comments from any of our audience. I did see one person earlier mentioned whether the vertical profiles, I believe that's what they were mentioning from Rick's presentation, could be provided, and that's something I can definitely, I think I can include when I put it together a summary, which I'll do and send out to everybody. So that'll definitely be something that's available. Was there, I don't know if there was any other questions or comments. I'll leave a few minutes to see if anybody'd like to ask a question either over the phone or in the chat box as well.
Marcia?
Yes. All right,
this is Sid Sperry.
Yes.
I might just mention that I see you've got the resources and the Spia Index website listed there. One thing folks need to keep in mind when looking at our index website is that we do use National Weather Service forecasts. That's where our forecasts come from, are directly from the National Weather Service. But as most folks know, the National Weather Service does not release publicly the digital ice grid information out past 48 hours. So while internally they may be looking at putting ice into their grids at 3 days, 4 days, 5 days, even out to 7 days, we do not, we're not able to get that information to put it and run it through our algorithms until only 48 hours out. So just know that, and when you look at those levels, and you might say, well, I'm hearing reports of ice 3 or 4 or 5 days out, and I'm not seeing anything here. That's the reason why.
Thank you, Sid. And actually, there was a question that came across here for you about the Spia Index from Rebecca Jennings of whether the impacts are relative to the area, like would your accumulation index be the same for Mississippi, or might it change for the actual location?
Well, we've actually tested the index against all types of utilities in every area of the country, from Washington State to New York State, as far south even as into Mississippi and Louisiana, when icing events occur there. And in all honesty, and I think this is a great credit to the National Weather Service and to the design of the algorithm, it's been very accurate, not only in the footprint, but also in the intensity of the of measuring how much infrastructure damage there could be. One thing I will say is that one of the purposes of the index is to raise the level of preparedness. In fact, that's the prime reason that the index was created. What I would hope to see over time is that as preparedness grows and utilities are able to respond more quickly, I would hope that those outage times could be reduced, say, in a level 5 event, which is the worst possible scenario of having people out for 10 days, 2 weeks, or more because of the level of devastation. By raising that level of preparedness, maybe that outage time can be reduced by several days. That's what I would hope for.
Thank you, Sid. Looks like there is some good discussion going on our chat board. And when I send out the summary, I will provide contact information from all of our presenters in case you would like to follow up with them or have any additional questions.
Marcia, I'm going to have to run. This is Sid, but again, if anyone would like to contact me, feel free. You have the contact information, and we'd be glad to visit with anyone if they have questions. But again, thank you for inviting me to participate, and it's been a real pleasure. Thank you so much.
Thank you, Sid, for joining us, and thank you for all of our presenters, for Carly and for Rick. I think there's been some great information provided today, and I hope everybody comes away with an appreciation of weather forecasting and a knowledge that this is a difficult time of year for not the weather, but the energy companies and all of that. So I also want to let you all know that the webinar has been recorded and will be up on our SCIP YouTube site later today or tomorrow. If you have not already signed up and registered for either this webinar series or we also have a drought webinar series, please go to our website, which is southernclimate.org, and you can find a registration form, and you will get updates about when we have these webinars, when recordings are available, and also when summaries are available as well. So in the end, we'd just like to encourage you to continue to spread the word to make sure all those dealing with the planning, preparation, or mitigation efforts with extreme events and hazards are involved. We encourage you to pass any of this information along, the PDF summaries, our webinar announcements, our YouTube recordings once they're available. And we thank you for your time today, and we look forward to continuing this conversation in the future.